Okay, how are you everybody who is in this class or in this moment? I'm very happy to have you and I'd like to take this opportunity to welcome you into a very interesting program of learning electronics and electrical workshop practice. If it's the first time, my name is Olenjolai. I'm very happy to have you today. And I would like to welcome you into the continuations of our program where actually we call them the workshops. And this is a very interesting course, especially for the beginner, electronics, mechatronics, biomedical engineers or technicians. And this is the very good starting moments because actually that in this course, you will be covering about the theory, the simulation, and also the practical implementation. So today we are going to have two parts, the small part of the theory, and then we'll go for the simulation part. So I'm very happy to have you. Just take your computer, have your computer beside it, and then have your fresh mind, have your pencil, have your exercise book, have your rubbers, and different materials that you need in order for you to accomplish this business. So I have some mechatronics engineering students in this class. I'm very happy to have them today, and let me appreciate their presence. How are you, students?
Fine.
Real fine?
Yes.
Are you ready for workshop 12?
Yes.
What the title of workshop 12? I just heard DC. Loudly.
Simulation AC and DC linear power.
Do you know linear power supply?
Yes.
Okay. So, let us focus on the, we call it overall schematic circuit diagram. Overall schematic circuit diagram of the goodness of this system. We have AC power and DC power. Of AC power, linear power supply. AC linear power supply. C linear power supply. So the overall schematic circuit diagrams, we say that here we need AC source. This is alternator. And then once we have this AC source, we need also a step-down transformer. This is iron core. This is the secondary coil. Excuse me. Then here we have the connections of power. So this is the secondary coil. Then we need to have 4 general purpose diodes from late rectifier unit. Please, students, draw these schematic circuit diagrams quickly. So then we connect the block of step-down transformer with the block of the rectifier unit. So this is the secondary coil of step-down transformer. This is diode 1, this is diode 2, this is diode 3, this is diode 4. Draw it quickly, it's very important. Some students say that I have the diagram. So this is the block diagram, so implementation schematic circuit diagrams of the step-down transformer. And this is the schematic circuit diagrams of 40 of rectifier unit. So we need the common ground here. Again, so we are going to implement the next part. The next part, we need the filter unit. Then we are going to implement another part where that we need to have a voltage regulator. Then a voltage regulator, it has 3 terminals. But the voltage regulator needs 2 non-polarized capacitors. So practically, we are going to use 1N407 general purpose diode. And this one also, it's 1N407, because now we have to talk practically. This is 1N4007, and then the names of this diode is 1N4007. So the electrolytic capacitor that we are going to use, we might use electric capacitor with a capacitance of 1,000 microfarad, or even 4,700 microfarad. So 4,700 microfarad. This one, it should be an electrolytic capacitor with capacitance of 0.3 microfarad. And we are going to design a linear power supply that will provide 5 volt, because we use 5 volt to power most of electronics parts. So we are going to use LM7805 voltage regulator. Again, at this part, so what did we say? We said that here we are going to have another ceramic capacitor to increase the stability of the output voltage, which is capacitance. So this is capacitor 1, this is capacitor 2, this is capacitor, let's say capacitor 1, capacitor 2, capacitor 3. So at this point, we expect to have the output voltage. So I told you that, how do we have this output voltage? So this is the point where that we are going to have something called a V out. But also we need the power indicator circuit, which you usually use a light emitting diode to indicate whether our linear power supply works or it does not work. So here we need a light emitting diode. But remember that light emitting diode and this resistor act as, so this is the resistance, this is R1, this resistance, it is, you may use 220 ohm. The capacitance of this capacitance 3, it's 0.1 microfarad. So remember that at this point, this is the point where we have V out, or this is the point where we draw the V out. And if you do remember that we say this V out, we have to use it or to connect it in the power connector or power bank. So this will be the positive power supply. So positive power supply bank. So we call them connectors. And for the negative, we can also have the negative power supply bank. So this is negative power supply supply bank. So resistor R1 and the LED, so we may use the red light emitting diode, red LED, just to indicate what, to indicate if our linear power supply works or it does not work. So this is schematic circuit, the overall schematic. I wonder, some physical students here are just watching over me. I say draw it quickly. The overall, because we are going to move to the next part soon. Overall schematic circuit diagram of 5-volt linear power supply. So in previous workshop, this is what we have drawn. Previous workshop, that's what we have drawn on the blackboards or on your exercise book. So today we are going to add value. And the value that you are going to add is actually will be focusing on measuring the choice of the testing points and also connections of the measuring instrument. This part you don't try it, you don't draw, you don't do anything. What's going on? You're just laughing. I said draw the schematic circuit diagram. You, why are you drawing? Draw it now. I'm drawing what? I told you as a serious mechatronics engineer, you must have a pencil. Tell your neighbor you must have a pencil. You are always drawing by using a pen. I want to tell you that even in the exam, you might draw by using a pen. And that is actually a good indicator for you. Are you really serious with the business that you are doing? Or you are not serious? Just have a pencil. That's the function of the pencil. And use rulers on drawing, because some of them are just, the lines are bending and roughly. Okay, so are you through? Okay, so while you are drawing, try to choose the testing point. Choose the testing point. Okay, so now, stop drawing. Now, let us add the values into our schematic circuit diagrams, overall schematic circuit diagram, by choosing important testing points. So for the case of the system like this one, we are not interested to just choose the testing points. We are very interested to choose reasonable and meaningful testing points. Are we together? Are we together? So this representing AC source. This is AC source. Representing what? AC source. So this is AC source. So the first testing point is this one. I say stop writing, look, and listen. Stop drawing, look, and listen. This is our first testing point. In this testing point, first of all, we'll be interested to measure the actual root mean square voltage that is being fed to our linear power supply. Remember that from this part, this is the part for our linear power supply. So this is the part for our linear power supply. So when we say about the AC source, in most cases, this AC source, we just see draw it from the wall socket. Right? Right? Yes. Yeah, so this is source of alternating voltage. So at this point, our measuring, the selections of the good measuring instrument is we need to have what? So for this point, we need to use AC voltmeter. AC what? Voltmeter. To be sure, because the range of voltage, our domestic voltage, it's 220 volt to 240 volt. So we have to be sure first of all. Are we together? Yes. That's the first testing point. To know the root mean square voltage from the source of power. From the source of what? Of power. Then we are done with testing point number A. Then here we are, testing point number B. So in testing point number B, we are going to have two testing points at this point. The first testing point will be interested this one. It is this one. So this first testing point we call it testing point B. What are we interested in? We want to know the output root mean square voltage of the step down transformer. Hello? I said stop drawing, stop doing whatever you're doing. Listen, watch. Then you will just see, take a note. So at this point, we are going to have also a C voltmeter to measure the output root mean square voltage of the step down transformer. And this is very important because sometimes the standard, in case of the simulation, the step down transformers, or we don't have step down transformers. For the simulation purpose, we just have a transformer. So you are the one, you've been given a chance as the user, either to set that transformer to be step down transformer or step up transformer. So that measurements of the output root mean square voltage from step down transformer or from the transformer is very important, because sometimes you might feed it 220 volt. If you don't change some parameters, especially primary inductance and secondary inductance of the transformer, then you feed 220 volt. At the outputs, you receive 220 volt, which is wrong, because the transformer did not do anything. And we'll see it in simulation part. In case of the hardware implementation or practical implementations or practical part, we don't have that challenge. But it's better to know what is output of each block, because this is the step down transformer block, this is the rectifier block, this is the filter block, this is the voltage regulator block, this is the load block. So the blocks that we have been teaching you in general, in detailed block diagrams of linear power supply, are very important to know what is its input and what its output. So you might know that what change of voltage or currents which have taken place within that block, when the currents or voltage flowing through that block. Are we together, class? Eh? Are we together? Are we together? Yes. According to the design that we have done in workshop 3, workshop 4, workshop 5 of electronics product fabrications, or in the modules that we call fundamental practical electronics engineering, then what we say that here we are going to use the step down transformer of 12 volt. However, that we have a number of step down transformers. Davy is Davy. Then we are very also interested to know about the amount of AC current. So this will be our testing point number B, where we are going to use a milliammeter, AC milliammeter, to measure the output current of the step down transformer. So this one will be 20C. Are we together? Are we together? Yes. So this will give us the input to the step down transformer. Then point B and point C will give us the measured parameters, or simulated parameters from the step down transformer. Are we together? Are we together? Then we are in rectifier unit. So remember that the output of step down transformer, the output voltage, and the output current of the step down transformer are the one which will be fed into the rectifier unit. But remember that in case of AC, we have something we call it root mean square voltage, and also root mean square current. And also you have another parameter which we call maximum or peak peak voltage or peak current. So we always, whenever we are converting AC, remember in case of when we are using alternating current in particular system, the parameter that we have to pay attention on is root mean square voltage. But whenever we are converting AC into DC, the important parameter is maximum or peak voltage, because it's the one that we are going to convert into the steered or constant voltage and constant current. Is it clear? It's not clear. Listen. I say, whenever we have electronic systems or electrical system that actually need to operate with AC power, the important parameter for that case, whenever there is a flow of AC, there is no any conversions of AC into DC, the important parameter is root mean square voltage and root mean square current. Right? But whenever we are converting, or we want to change, or we want to convert AC into DC, the important parameter for that case is maximum voltage or peak voltage and maximum current or peak current. Are we together? So if you refer what I taught you in theory, in workshop 3, and especially workshop 4, we, after measuring this output voltage of the step-down transformer and output currents of the step-down transformer, when we want to measure the output of the rectifier, we have to change this root mean square voltage into the maximum voltage. Why? Because, for instance, if we measure 12 volt, at this point we might measure 15 volt. So that 15 volts, where does it come from? Well, so that 15 volts is actually its maximum current, because this is the root mean square voltage is 12 volt. If you convert it into maximum voltage, then you get 16.20 something. So it means that this will be the end of use. So we have only 2 points where we have to use root mean square voltage. This point A and this point B. From there, for instance, that what will be received and sensed by this rectifier unit is maximum voltage and maximum current. Why? Because remember that AC is continuous signal, so it's alternating. DC, it's constant signal. So if it is constant, it means this DC always corresponds with the maximum voltage or maximum current in AC. That's why we need to know the formulas. That's the use of the formulas and the equation. Because remember, the AC voltmeter measures the root mean square value. Right? But in case that you want to change the AC into DC, you need maximum value. How can you achieve it, or how can you get? You have to measure the root mean square value and then use the formula to convert it to maximum voltage. Class, are we together? Are we together, class? Are we together? Yes. Then, at this point, then we are done with the step-down transformer. At this point, also we are going to have another testing point. This testing point, we call it testing point, letter D. In this testing point, what's our interest? Our interest is the measurement of 40 of voltage. This you can call it V at point A, V at point B, V at point D. But again, we need to know about current. So we have another testing point about current. So for this case, we need to have a DC milliamp. No, I think that these are important. The issue of current we may just not deal. So at this point, we might deal with DC to measure the amounts of AC voltage which has been changed into DC. Right? Right? But remember that I told you theoretically, we have been taught that a rectifier converts AC into DC. But I want to tell you that practically, rectifier converts some percentage of AC into DC. But it fails to convert some of the percentage into DC. So that's why at this point, we are going to have two important points. One point, we have to measure the DC, which has been rectified by the rectifier. And then another point, we have to measure and rectify the AC power, or the AC components which rectifier fail to change from AC into DC. Are we together? So at point D, we are going to use DC voltmeter. At point E, we are going to use AC voltmeter. Are we together, class? Are we together? Yes. Then, remember that all of these measurements has to be done block after block. Then, next, at this point, we say that, okay, so this is another point. This is the filter. So at this point, we might need just two parameters, or we might have two testing points. The first one, we might have point F, where that we need to know the voltage, the output voltage after rectifier. But also at this point, we need to know the current. So we need to also connect milliammeter. So this will be testing point A, B, C, D, E, F, G. Are we together? A. Remember that the output of rectifier is the input of the filter. The output of the filter is the input of voltage regulator. Right? Right? Then, for that case, we say that our another point of interest is this one, this point. So this is A, B, C, D, E, F, G, H. So, and also we have another testing point here, another testing point where we'll connect the milliammeter. So at this point also we want to know about output voltage from our output voltage of the regulator unit. And this point we need H, A, B, C, D, E, F, G, H, I. So this is point I. We have the COT milliammeter. To know the output voltage or the current, to know the output current of the regulator unit. That the expert was slumbering. Then, this is another testing point. A, B, C, D, H, I, J. So at this point, we need to know what to measure voltage across resistor. Then again, we have another testing point here. So in this testing point, we need to know voltage across LED. But also you can have another testing point here. However, that this milliammeter and this milliammeter will give us the same value because they've been connected in the sensor. No need of this testing point. So HI, J, so this is point J. So this is J, K, yeah? Okay. So you can, when you analyze this circuit, from this point to this point, it's AC. But also theoretically. But practically, what you'll notice, from this point to this point is still AC. Where will you find DC? From the filter to this part is where we have DC power. Are we together? Are we together? So simply we say that practically, this is the point. This is the part where we have what? We have DC. Then, this part, practical. This is the part whereby we have what? We have what? AC. So how many testing points do you have? 100? How many testing points do you have there? 11. Huh? Yes. Okay. So testing, the first testing point, second testing point, third testing point. Fourth, fifth. 6, 7. 8, 9. 10, 11. This is indication part. But this one will be representing the load. This point and this point, this we call them power bank. They will be supplying power into different parts of your electronic circuit. Class, are we together? If you have any question about what we've discussed, ask it. So you could notice that you will have a table of results with how many values? 11 values. But unfortunately that for yourself you came with no any table 40 result. Yes.
Measuring current. Yeah, just measure the point G. But the question is, this capacitor in parallel connection. That means the current from the rectifier is not equal to the point the test point G there. So why are we measuring at point G while there are some current which
Okay. I understood your question. So there's one student say that capacitor 1 and even capacitor 2 or capacitor 1, it's parallel with this network. Right? That's what you say. Capacitor 1 is parallel with this network. That is true. But remember that our intention for this system, for the entire schematic circuit diagram, is to convert AC into DC. So our main focus here is DC. So at this point where we have a junction, what he expected that the current at point E is not equal to the current at point G. Why? Because we have a junction here. So if you have a junction, this is one of the route, this is another route. Then that is true. At this point, really, we have a junction. So at this junction, what actually we expected to see, practically we expect to see a AC component and DC component. So the AC components actually have a choice either to flow towards the voltage regulator or to flow towards the filter. And I told you that because the filter will be providing very small resistance against the AC. So all the AC will be flowing through the filter and going to the ground. For that case. But remember that the capacitor, or electric capacitor, does not allow or provide infinity capacitive reactance against the flow of DC. So at this junction, only DC power will be allowed to flow towards the voltage regulator. Are we together? So this one, it will be DC what? DC milliammeter. If you want to measure current here, it's fine also. It's okay. But in case you want to measure current here, you have to use two measuring instruments. DC milliammeter and AC milliammeter. Why? Because here we have two components, AC components and DC components. Are we together? Are we together? Are we together? Yes. Another question? You have a question? My friend there? Hello? Do you have a question? Thomas? Baraka? That voltmeter, yes, okay. Baraka asked me a question, and his question is this one. Look now, very important question. Here we have 4 semiconductor comp devices. We have 4 diodes, right? 1, 2, 3, 4. Then Baraka asked me a question. Why do you use a single DC voltmeter and a single AC voltmeter to measure voltage across diode 1 and diode 2 while, stand up, while we have 4 diodes? Why should we not measure voltage across diode 1, diode 2, diode 3, diode 4? That is Baraka's question. Why did we measure only voltage at one point, which is common cathode and common anode? Why? Who can try? Who can respond that question? Or who can answer? Who can answer that question? Okay. The answer is very simple if you referred what I told you. Listen. The answer, there's no need for you to measure voltage across diode 1, diode 3, diode 2, diode 4. Why? This voltmeter actual or these two voltmeters will measure what is actual flowing or what is dropping across these diodes. Why? Remember that the 4 diodes that we've used to design or just to build a rectifier, they are not conducting current at the same time. Just the 2 will be in forward bias, they will conduct current, and 2 will be in reverse bias at that time. Within a fractions of second, then the other two diodes which were in reverse bias becomes, or actually that be in forward bias, while the 2 diodes which were in forward bias are in reverse bias. So these two, the DC voltmeter and AC voltmeter can actually measure the voltage, the output voltage of this rectifier. And if you do remember that I told you that, for instance, if this part is positive, so it has a positive half cycle. On these sides, we have negative half cycle. Then what I told you that, so this is positive and this is anode. So if this is the anode, this is cathode. So if that's the case, it means that anode and positive have been connected. So now the one will conduct power, will conduct electricity by that time. Then, for this case, this is the junction. Either that power might flow in this network through the 1, the 2, or the 4, through the 2 and the 4, or might flow towards this direction. So it won't flow through the 2 and the 4. Why? Because this is positive voltage or positive power. So positive power is connected with cathode. So this diode 2 will be in reverse bias. Okay? So if it be in reverse bias, here there will be high resistance. So what will happen? So this positive power will flow through the voltage regulator and circulating, passing through the resistor, pass through the diode, and then returns up this point. Here we have also a junction. Remember that this is positive. Remember that this is negative. At this point is negative. So for that case, we say that, so either these positive currents might be flowing this through diode 3 or might be flowing through diode 4. So this is positive. So diode 4 will be inverting, will be positive. Diode 4, the anode of diode 4 is connected with the positive terminal of the battery or positive terminal of the AC source. At that time, remember that we have negative. So negative is connected with cathode. Okay? No, negative for that case, because here we have negative. So this is negative connected with cathode. And this is positive. So diode 4 will conduct power. And then this is positive now. So if it's positive, this is anode. Okay, so if this is the anode, so it will prefer to come and flow this way. That's when the positive half cycle is given from this wire of the step-down transformer, while in this wire we have negative half cycle. So for that circulation, diode 1 and diode 4 are in forward bias, while at the same time diode 3 and diode 2 are in reverse bias. Right? Against alternating voltage change its direction. On the, at this point, we'll have negative half cycle, while here we have positive half cycle. Right? So the positive half cycle, so here, remember this is cathode, positive half cycle. So if this is cathode, but this is anode. So positive half cycle, so this diode 2 will conduct. Then at this point, we have a junction. With the power, AC power to flow this direction, so to flow this direction. But remember that this is positive, and this is cathode, so it will be in reverse bias. So this will be in reverse bias. So what the preferred direction, the currents will be flowing through a voltage regulator, through the diodes, and then it returns. And once it returns, then at this point, either it may go this direction or this direction. So this is positive, and this is anode, and this is what cathode. So it means that the power will be flowing through this diode because it will be positive, and this is anode. Right? Once it flows, then it reaches at this point and then return to the step-down transformer. So what I told you that day, I told that if this is positive, then power will be flowing this direction, then flowing in these directions, then returns at this point. Once it returns at this point, then flowing through diode 4, and then returns to the step-down transformer. When the directions of the AC reverse, okay, so this is positive. So then, this is the directions of power. Flowing through the 2, flowing through the voltage regulator, flowing through the limiting, current limiting resistor, flowing through the diodes, flowing through these directions, and then this is the point. right? So flowing through the 3, then returning to the secondary coil of the step-down transformer. That's how power circulates. Are we together? So this DC voltmeter and AC voltmeter will measure voltage across the 2 diodes which are in forward bias. But you'll be measuring AC and DC voltage all the time. Why? Because when the 2 diodes conduct, other 2 diodes they don't conduct. When the other diodes conducts, the other 2 diodes are not conducting. So actually, there is alternations, alternations, but it's very high speed alternation. Why? Because remember the frequency of AC is 50 Hz. So it means that there's the number of complete cycles, how many? 50 complete cycles. So if you have 50 complete cycles, it means that we have 50 half cycles, positive half cycles, and 50 negative half cycles. Class, are we together? Yes. Is it clear? Is it clear? So now you may have table 40 result for this schematic circuit diagram. So if it is clear, now let us go to the simulation part. Okay, my dear students, this is the time now we have to practice, or we have to move to the next part of actual drawing and simulating the AC to DC linear power supply. So we'll be just following the 7 steps on drawing the schematic circuit diagram. But for this particular purpose, because we have a AC power part and also we have DC power part, we'll be having a focus which is actual that will be drawing block after block. So remember the 4 or the 5 blocks of the linear power supply. The first one is step-down transformer. The second one is rectifier unit. The third one is filter unit. The fourth one is voltage regulator unit. Then the fifth one is load. So why should we not draw the entire circuit or the overall schematic circuit diagrams of this linear power supply and then do the measurements? The reason is, when we connect, for instance, the block of rectifier unit with the block of filter unit, some of the parameters will change, especially for the AC and DC parameter will change. So that's why that at the beginner, I would like to ask you to draw and do the measurements of each block before you move to the next block. You may select it or you may pick all the components that you need. But in case of placing, you have to place just for the particular block and join them together and then do the measurements. Then you connect another block and do the measurements and then you continue. Are we together? Are we together? Are you ready for that? So for the physical students and online students, I ask you to pay attention. For the online students, because you have a video, you may just check what I'm doing and stop the video, then you do the practice. Then I move to the next part, you check it, then you practice. So step by step, you should not watch the entire video. For the physical students, they can actually, because you have a projector, they can actually just follow along and then do the practice. So then the first step, we have opened the new project. That's the new project, but I didn't save it. So file, then let me just save it. Save the project as. So this one, just let me call it linear power supply. Linear power supply unit. Where am I going to save? In desktop. Then I have a folder called the Proteus. So here it is. Then open it. Then next, let me save it. So now we have already created we are done with the first step. We have created the new page. Then now we are going to the second step. Let us go and pick the electronics components. Students, I said, stop drawing, look and listen. Look on the blackboards and listen and take a note in case that you forgot something. So the first components which we need, it's a step-down transformer. No, it's alternator, which will be acting as AC source. So you just write alternator. So alternator, here it is. Then I've already placed where? In the object selector window. The next components, I need transformer. So you have to write transformer. Transformer. So the next component is transformer. Just to choose this one, number 3, which is simple transformer. You may take a note about the choice of transformer because there we have different types of transformers. Then this is simple transformer. Then we are done with those 2 components, we are done with the part of step-down transformer. The next part, we need what? Rectifier. And rectifier, we have 2 options. We may implement the rectifier. Students, I said, attention please. Attention, look on the blackboard. Then we may implement the rectifier by having rectifier IC, or by selecting rectifier IC or integrated circuits, or we may implement the rectifier by using individual diodes, general purpose diode. So you are going to implement the rectifier unit by using rectifier or by using general purpose diode. So the general purpose diodes, according to the schematic circuit diagrams, is 1N4007. You just write 1N4007. Then you have this one. The specification, this one is actual that has a voltage of 1 kilovolt and current, maximum current is 1 ampere. So in case you are designing a linear power supply which provides more than 1 ampere, these diodes will not fit for your design. You have to check other diodes which can withstand more than 1 ampere. That's the precaution. Then, so I have already the 4 diodes. I need the filter part. So the filter part, we need the 4,700 microfarad. So we just write 4,700 U. So U stands for the microfarad. Then I have to be careful on choosing it. I have this one of the 10 volt. Let me choose the one with 25 volt. So this is our electrolytic capacitor with a voltage ratings of 25 volt. Then next, we need a capacitor, a non-polarized capacitor, which is 0.33 microfarad. So for that case, we just write 33 picofarad or nanofarad. Why nanofarad? Because 0.33 microfarad is equal to what? 0.33, I think that we have to write 3,300 nanofarad. 330 nanofarad. Because 1 microfarad is equal to 1,000 nanofarad. Right? You have to be careful. You might find something there and then you say that component is not there. So we have it. This one, which is 330, this one, 330 nanofarad, which is equivalent to 0.33 microfarad. So select that component. Oh, sorry, I took the other ones. Okay, that's fine. Of the 16 voltage, fine. Then another component is voltage regulator. Voltage regulator, we said that we are going to design a linear power supply that will providing output voltage, early output voltage of 45 volt. So according to the manufacturer or the voltage regulator IC, it's LOM7805. But in Proteus library, we don't have LOM7805. We just have 7805. But when you go and buy the physical voltage regulator, its IC number, it's LOM7805 or LOM7806 or LOM7809 or LOM7812 or LOM7815, LOM7818, LOM7824. Those are positive fixed voltage regulators. Okay? So in Proteus, we just write 7805. We don't need to write LOM. If you write LOM, you won't find that. Those are the shortcuts that I'm teaching you. So we have it there. So it's a 5 volt fixed voltage, but it's providing maximum of 1 ampere. So here it is. Then we need a non-polarized capacitor of what? 0.1 microfarad, which is equivalent to how many nanofarad? 100 nanofarad. I have some physical students here, but actually, they are just listening and wait the information. 100 nanofarad. So where is it? This one. Then the next component is light current, we call it current limiting resistor. We say 220 ohm. So 220, we just write 220 R. Then we go for the category 220 R. We move the category resistor 0.5. This is 220 ohm. Then another component is what? Red light emitting diode. So write LED, then we write dash or dash, then we have red. So here it is. So we have already picked all the electronics components that we need for our design. So then we click OK. So next, place the electronics components. We have to start with what? Alternator. So here it's our alternator. I told you that in order for you to design this linear power supply successful, deal with each part separate. So this is the alternator. We expect this alternator to provide a root mean square voltage between 220 volt and 240 volt. So how can we do that? We have to go to the visual instrument part and select what? AC voltmeter. So this is our AC voltmeter. So it is our AC voltmeter. Let us connect it to this alternator in order to do the setting. So there it is. We don't know the frequency, we don't know the parameters of alternator. For instance, for this case, if we run, we could find that. So you see the measured voltage. Hello? So you might find that that is alternating voltage. So once you see that, you have to notice, because I taught you the trick. Means something is wrong in that alternator. Salama, let us stop our simulation. So let us come to the properties. Just double click. Then the part reference is not important. We have been asked to write out just to actual that to write the amplitude. What the maximum voltage we have to fit there to get 220 volt? You forgot. 300. 311. 39. We want to get 220 volt. Root mean square voltage. Or you need 240. Okay, so my students here say we are familiar with 240. So 300, 39.20, 1. All right? Then how about frequency? 50 Hz. So is everything okay there? We click OK. Then let us run our simulation. So you see, what the measured root mean square voltage? 240 volt. Are we together? Are we together? Then let us stop our simulation. Then we need to take a simple step-down transformer. Simple step-down transformer. So you have to come back to the component mode. So where is our transformer? This one. So we have our simple, or we have our, remember I told you that is neither step-down transformer nor step-up transformer. Students, I say, look on the blackboard first. Hello? Hello, Jada, with your colleagues? I say, in Proteus, we don't have neither step-down transformer nor step-up transformer. And maybe you can have an argument that, sir, it's not true. Let us see. So, for this case, let us take another AC voltmeter to measure what we get from this step-down transformer. And let us connect the step-down transformer to the AC source. And here it is. And then let us connect this AC. Okay? Okay? So it's just like we took the physical transformer and connected to the domestic power source where we get it from the socket. Students, I say, look. So let us run our simulation. So if this is the simple step-down transformer, we might find that the output root mean square voltage should be less than the one which has been taken from the source, right? If it step up, we have to expect that the output root mean square voltage is higher than the one which has been provided in primary. So for that case, let us run. So if you run, what do we get at the output? A 240 voltage. So the input voltage is what? 240 volt. The output voltage from the transformer is what? That's why I told you that this is the ideal transformer, which is neither step down nor step up. Right? Nothing has been stepped down, nothing has been stepped up. What you fed is what you get at the output. So the number of primary coil for that case is equal to the number of secondary coil. Are we together? That's why I ask you to listen and make a follow-up before you practice. So then what we have to do here is simple. We have to change the properties of this ideal transformer. How can we change the properties of this ideal transformer? We have to remember the theory. Hello? We have to remember the theory. Which theory should we remember? If the transformer is step-down transformer, the number of primary coils should be higher than or greater than the number of secondary coil. Or the number of turns in secondary coil should be less than the number of turns in primary coil. Right? Right? So how do we define it in simulation? Simple. The way we define simulations is actually by using something or parameter we call it inductance. We have primary inductance and we have secondary inductance. So there I've right-clicked the ideal transformer, and then you see that we have primary inductance, which is 1 Henry. That H it is SI unit of inductance, which is Henry. And also in secondary inductance, we have also inductance of 1 Henry. So that's why I told you previously that it was ideal transformer, where the number of turns in primary is equal to the number of turns in secondary. Right? So the primary inductance in primary coil is equal to the secondary inductance in the secondary coil. So what you have to do in order, so we have been given a choice. We've been given a chance to either to make it step down or to make it step up. So to make it step down, we have to lower the primary inductance. It means that to reduce the number of turns. If you reduce the number of turns in secondary coil, if you reduce the number of turns in secondary coil, its secondary inductance will be decreased. Right? Because remember that the inductance is that proportional to the number of turns. Okay? Okay? So, for this case, in the secondary coil, we are going to have 2.5 millihenry. 2.5 lowercase millihenry. So, it means that once we change that parameter, the primary inductance is 1 Henry. Say 1 Henry. And secondary inductance is what? 2.5 millihenry. So the secondary inductance is less than the primary inductance. Right? So from there, we have already changed the number of secondary coil and make the step-down transformer which provide the output root mean square voltage of 12 volts. If it is 15, you have to change the parameters. If it is 24, you have to change the parameters. If you want to make it to step down 240 to 9 volts, you have to change what? Just see one parameter, which is secondary what? Inductance. And take a note of that, because it causes a lot of challenges, especially if you forgot. Okay? So now let me click OK, and then let me run the simulation. So what do you have there? You have root mean square voltage of 40? 12 volt. Okay? So you see you have input voltage 240 and output voltage is 12 volt. Practice up to that point. Okay, so for these times we have implemented the first block where that we have our step down transformer and the input voltage is 240 volt. The input root mean square voltage is 240 volt. You may note it in your table of result. For the simulated, that's point T, because we had the point A. So here it's point A. So its measurement, root mean square voltage, it's 240 volt. Then another testing point, it's testing point B. No, another testing point B, which is output root mean square voltage. So for our case here, it's 12 volt. But we have another testing point where we have to measure the output current or output root mean square currents of the step down transformer. Do you remember that point? Yeah, that is point what? B or C? Point C. Well, so let us stop our the simulation. Let us go to the visual. I say the attention, listen, watch. Listen, watch. I'm going to draw this circuit quickly, but I will show you some technical challenges that you might experience one day. Those are the latecomers. Okay, so for that case, we say that let us take our visual instruments. We call it what? AC ammeter, and then connect it here, and then see what's going to happen. So you have it there. Then let us break down this wire and take this one, then connect there. Okay, we said that let us plug this AC voltmeter, because an ammeter should be connected in series. If you do remember that we expect to measure small amounts of currents because we don't have a load that consuming current. So I told you that once you have this AC ammeter, it's better to change it into AC milliammeter. So there we have AC milliammeter. So let us run our simulation for this first block. What do you see? We see 0 volt. What does it indicate? Or does it teach us? If we measure the output root mean square currents, we get 0 milliampere. What do you learn from that concept? Ask your neighbor. Why do you have 0 milliampere there? It means there is no flow of current. Is that the open loop or it's a closed loop? What's going on there? Ask your neighbor. Yeah, and whenever you ask your neighbor, it's just like a shocking question. What's going there? Ask your neighbor. Hey. So that is your neighbor. That lady, it's your neighbor. So you may go there and ask her. Yes, you go there. So what's going on there? So we measured the output root mean square current of the step down transformer. It's 0. If we could have been using AC ammeter, we could say that maybe there's a small amount of current. But we have used the AC milliammeter. So you expect the current to be measured in terms of 40 milliammeter. Maybe you can have a doubt, say, maybe the current flowing there, it might be in microampere. In microampere. So let us stop the simulation and let us change this one into micro AC, microwatt. We have now AC, still AC milliammeter. So AC microammeter. So AC microammeter, let us run the simulation. So at least there we see that we have 0.12 microammeter. 0.12 microwatt ampere. So it's a very small amount of current. Why do you have that very small amount of current? What did your neighbor tell you? Oh, your neighbor was quiet? Your neighbor was quiet? And how about you? What did you tell your neighbor? If your neighbor was quiet. Both of you were quiet, eh? Huh? Each was quiet. Okay, so the reason is hello there. So the reasons why do we have 0 ampere or 0 milliampere or 0.12 microampere? The reason is there is no any load that consuming current. Okay? There is no any load. Those primary coil and secondary coil, they have a very small internal resistance. Okay? Okay? Okay, fine. So let us stop our simulation. And then let us just use the AC milliammeter. Then let us build another block, the second block, which is the rectifier, right? So we have to come back to the components mode. I say these students, stop drawing, listen, and watch. Once we are done for the physical students. But for the online students, you may just watch the concept, stop the video, practice it, then continue. But for the physical students, I ask you to make a follow-up because you have no any video to stop it there. Then the next block, we just need OT 1N4007 OT general purpose diode. So you have to implement OT, the rectifier unit. So where is it? So you can check this one. Okay? So let us have it. Rotate it. So we have that one. Then next you can copy. Then we have the next the second diode. This is the third diode. And here we have the first diode. So then, next we've placed the 4 diodes. Let us join them. How do we join them? This will be our common cathode. Then let us join the first diode and second diode. And let us join the second diode and the third diode. Let us join the third diode and fourth diode. Okay? Okay? According to our overall schematic circuit diagram, we say that we have to take one wire from the step-down transformer and connect it between diode 1 and diode 2. Okay? Then next we have to take another wire from the step-down transformer and join it, or let me just say actual that thing. Have it here and join it between the anode, the cathode of diode 3 and the anode of diode 4. Are we together? Are we together? Yes. So because we have a rectifier, we need to go to the terminal and choose the groundy terminal. So for this case, we need the ground terminal. Are we together? Next, we need the measuring instrument. Theoretically, we have been taught that a diode rectify AC into DC. So let us take DC voltmeter and measure the output voltage of this rectifier unit. Hello? So now let us join our AC voltmeter before we join the ammeter. So this is our DC voltmeter. It will measure the output voltage of rectifier unit. I say the physical students, attention, look on the screen. Then, for this case, I think everything is okay and everything is clear, right? In case you didn't understand, you can view this video, check it, or watch it several times. Let us run our simulation. When we run our simulation, what do we measure the output DC voltage? It's 2.5. 2.5 to 2.5 It's range 2.50, 2.52. So let's say it is 2.51. So that is simulated values. And that is testing point, letter what? Letter what? D. So write it. That's the results that we have found. When you did these simulations yourself, most of you found the 5 point something. Most students measured the 5.07, if I'm not mistaken. So I don't know where did you get it. But that is good because you have to practice. And it's better to learn from mistake. So that is output DC voltage. From what? Rectifier unit. Or from the bridge rectifier system. Are we together? Eh? So the question is, we have a root mean square voltage output, the input voltage to the filter, it's 12 volt, but it's root mean square volt. I told you that we don't convert root mean square voltage into DC voltage. What actually we have to convert into DC, it's maximum or peak voltage. So the input voltage of the rectifier, we have to define it as maximum. Maximum output voltage of the step-down transformer. Are we together? Are we together? So how can we get the maximum output voltage of the step-down transformer? It's simple. Just take 12 volts multiplied by under root of 2. What do you get? 12 volt multiply, you have a calculator there. 12 volt multiplied by under root of 2. Pardon? 16.97 volt. That is maximum output voltage of step-down transformer, which it is input voltage of what? Input maximum voltage to the bridge rectifier unit. Are we together? Yes. So there in that rectifier unit we have how many diodes? 4 diodes. Say 4 diodes. 4 diodes. How many diodes conduct at a time? 2 diodes will be in forward bias and 2 diodes will be in reverse bias. What the potential barrier of the silicon diode? 0.7 what? Volt. If you have 2 diodes in series that in forward bias, 0.7 volt plus 0.7 volts makes what? 124 volt. So in order for the current to flow through the diodes, the 2 diodes that in forward bias, it means that the supply voltage should be greater than 124 volts to overcome the potential barrier of the 2 diodes that are in forward bias. So what will be the potential drop across the 2 diodes? 124 what? Volt. 16.97 volt minus 124 volt. What is output? What do you get? 15.57 volt. So at the output of this bridge rectifier, we expected it theoretically to measure 15.5 what? 15.57 volt. But there we measure 2.51 volt. What happened? And that's the importance of theory. That's the importance of what? Of theory. Because theoretically, across those diodes, we have a potential drop of 1.4. Then the maximum input voltage to the bridge rectifier is 16.97 volt. So you expect the potential drop here to be 124. What we are supplying? 16.97 volt. So if you have a potential drop of 1.4, we expect to have 15.57 volt. But now in simulation, we measure 2.51 volt. What happened? So that's why you have to learn the theory of the concept before you go for the simulation, before you go for the calculation. Okay? 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 Okay. So, why do we have two 25 1 volt? The answer is simple. Remember that 16.97 volt, it's AC, it's alternating current. It's maximum voltage of alternating voltage which has been supplied to the bridge rectifier unit. So finally at the output you have what? 2.5 volt, which is DC. So how about the remaining? Simple. The remaining maybe it is AC components. Are we together? Are we together? Take 15.57 volt minus 2.51. What do you get? What do you get? Hurry up, please. 13.04. So it means we are missing 13.04 of the C voltage that we expect at the outputs of the bridge rectifier. That's why I told you that electronics is not tomato. Tell your neighbor, electronics is not tomato. Or tell your neighbor, electronics is not like a chips. Your mind has to be involved. Otherwise, tell electrons, bye-bye, I loved you, but now I changed my mind. Let me go for the business, especially in Dar es Salaam. Business, what? Sit. Because in business, simply you just need what? A frame, right? Especially in Kariako. You made life. Okay. So, it means that from there, because if you don't do measurements after 20 to point, you have no reasons. And then let us check. Our AC voltmeter, milliammeter still, or milliampere, still measuring the 0.00. So there is what? Some AC components from the simulation concept. While theoretically, a diode rectify AC into DC. That's what you've been learning in O level and the A level. But from there, you have to argue. We just give you a concept. Okay, so to realize if there's another AC component, it's good. Let us take AC voltmeter and then connect it to measure some of those AC components. So this is our AC voltmeter, right? And that is testing point. Okay, we are filling the table. Just relax. So let us run our simulation. What is measured root mean square voltage? What is root output root mean square voltage of the bridge rectifier? What is it? Remember, AC voltmeter measure root mean square voltage. So what is it? What do you see there? 11.4. What were we missing from the DC? 13.0. My brother, you told me that now you don't mention anymore. 13.04. But here we have 11.4. But again, something happened there. I don't know if you notice it. So the output DC voltage has been decreased to 1.44 volts. What happened? For you, don't reason because you're a Bongolan student. What we are just saying, sir, add the components, and let us finish the business. Fine. So, to get the response about what we have, just take 11.4 multiplied by under root of 2, because that is the root mean square voltage. 16? 16.1? 2. So 16.1, 2. Then plus 1.44? So at least it's near by what it has been supplied. So I think you saw what happened, yeah? Okay, so we are done with the block of bridge rectifier. We have seen what is going on. So for the filter unit, we have to stop our simulation. We just need the one electronics components that is called the electrolytic capacitor. And the main function of that electrolytic capacitor or this filter is actual to filter all the AC components that we have measured the AC components which bridge rectifier failed to convert into DC. So we discussed about the filter. I talked about capacitive reactance in the previous session and how we can calculate. And then we realized that electrolytic capacitor provide small amount of capacitive reactance against the AC power, but provide what? Infinity resistance against what? DC power. So when we introduce the capacitor and connect in parallel with a bridge rectifier, then we are going to have two networks. One network will be towards the capacitor, the other network will be towards the voltage regulator. So you see all the AC components will be drawn through the capacitor towards the ground. Okay? So according to what we have, so before we add what the output, so from that schematic circuit, what the output of the bridge rectifier. What the output voltage of bridge rectifier? DC voltage is 1.47, right? And the AC voltage is what? 11.24, but root mean square. What is maximum voltage? You said what? 11.4 times under root of 2? 16.20? 16.20? So output maximum voltage of bridge rectifier is 16.22 volt. So remember that the output of the bridge rectifier, it's an input of the filter unit. Are we together? Are we together? So what are we going to feed on the filter? It's 2 voltage. 16.22 volt AC and the 1.47 DC. Are we together? Are we together? Check your neighbor. Your neighbor is not concentrating. Do you see your neighbor? Your neighbor is chatting and sitting like a big boss. So we had the electrolytic capacitor. So let us come back to the components mode. We have our electrolytic capacitor, which is capacitance is 4,700. So this is our electrolytic capacitor. I said, attention please, look on the screen. So I rotated it, and after rotating it, I have to connect it in parallel. Once I connected this electrolytic capacitor, my dear students, I want to tell you that the parameters, the output parameters, or the output voltages of bridge rectifier will change in values. Are we together? Are we together? Before we do the measurements about the output of the filter unit, once we run the simulation, you will see something wonderful. What do you see? I said, stop writing, stop drawing, look on the blackboard. What's going on here? So let me run. 1, 2, 3. Run the simulation. Run the simulation. I think you see something different. Before we measured what the output voltage of the filter. So now, from the bridge rectifier, the output DC voltage is 15.8. The output root mean square voltage is 15.8. That's why I told you, in electronics, we design step to step. For you expect to draw the entire overall schematic circuit diagram of linear power supply and then do measurements. I want to tell you that you will miss a lot. Okay? Remember that we didn't change anything. And I forgot one component. I forgot one component that's very, very important. I forgot one component which is very important. You know the components that I forgot? Something we call it single throw, single, or single pole, single throw. I forgot the switch. Single pole, single throw, switch. So where is it? Here it is. So I forgot it. So let me connect it here. So let me delete the wire. Because the switch is very important for the power supply. It's not the formula that the switch always should be connected on top of the circuit. Because some students say that, what happened? You usually connect the switch on top. Okay? So if we run our simulation for this time, then let us close our switch. Run the simulation. Let us close the switch. Then we see that what we saw. Hello, backbencher students. Then, remember that if we disconnect this capacitor, just let us disconnect it from the network. Then if you have our measurements, this is our previous measurement. Do you remember them? Eh? Do you remember? Okay. So if that's the case, then let me connect the wire. But before we measure the outputs of the filter, when we measure the outputs of the rectifier, so from there you will see the power of the filter. Then we say, okay, fine. Let us continue. Let us measure the output voltage of the filter. Let us go to the visual instrument. The output voltage of the filter, we need two measuring instruments. We need what? We need AC voltmeter. We need what? We need also DC voltmeter. So let us measure the voltage, the output voltage of the filter. Then this is DC voltmeter. Let us measure what we get in the output. Run the simulation. Do you see again? What do you see? So from there, the input, DC voltage to the filter, is equal to the output, DC voltage of the filter. The input, AC to the filter, is equal to the output, AC to the filter. Are we together? Are we together? You could not understand what's going on there if you have never gone through the theory. So, we have already implemented the steady block, which is filter unit. Now we're going to implement another block, which is the force block, which is voltage regulator unit. Do you have any question of that part? I think we need also to measure current before even we go for the force block. So we need what? So you know that now the current is DC. So let us connect the ammeter in series. This is the one of the testing point that we had. And let us have AC or DC milliammeter. So, you see? So what is current? The amounts of current flowing through the bridge rectifier and filter, 0 milliampere. Why? It means all of those electronics components, they have a very small internal resistance. So they have very minimum electric consumptions or consumption of power. Okay? 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 So this AC milliammeter, this DC milliammeter, it's testing point, Roman what? You forgot? You have been confused there? Yeah, you've been confused because I know. For you, you drew the overall schematic circuit diagrams of linear power supply, and then what you've measured is completely different from what you have been measuring. Wonderful. Let us stop the simulation. Then, so after designing, we came up and read the data sheets of voltage regulator. We came up, since the voltage regulator consists of 3 electronics components. One is voltage regulator, IC, and also 2 non-polarized capacitors. Right? Right? So let us go to the component modes and then choose the LOM 78 0 T 0 5. So then this is the ground terminal. So this is input terminal, this is ground terminal, this is the output terminal. Then we need another ceramic capacitor of 330 nanofarad. So this is the capacitor. Let us rotate. It does not have any polarity. Then we need another capacitor whose capacitance is 10 nanofarad. Let us rotate it. So we have our voltage regulator unit. Okay? 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 So the output of filter unit, it's the input of the voltage regulator unit. Are we together? Then next, what do you have to say or what you have to do? Then we are going to pick the measuring instrument. So we know that the output of voltage regulator, it's DC. So we want to measure the output voltage of voltage regulator. Here it is. So that's one of our testing points. Okay? Okay. Let us run our simulation. So once we run our simulation, so what do we measure now? So, okay. So once you see 0, 0, 0, there's a problems of connections of this milliammeter. Right? What problems? Let me figure out. Let me figure out about the problems that we have. This milliammeter is not connected. You see? Have you seen it? Okay. So then we say, if you want to realize, let us connect it in series. And connect this one at this point. Then let us drag it, return it to its position. So let us run the simulation. So there we have. So the input voltage of the voltage regulator, it's 15.4 volt. You see that even the voltage across the filter unit have been decreasing in some decimal points. Previously it was what? 15.8. Now it's what? 15.4. I don't know if you have noticed. Those are the challenges that we encounter for the simulation part. Are we together? What the output voltage? It's 5 or 5.0 volt. We still have the load part, which is the power indication part. Okay? Okay? But I want to show you something which I warned you from the beginnings before I implement the indicator part. I told you that for the behavior of voltage regulator, even if you use the ideal transformer, you will have the output voltage in simulation. You will have the same output voltage. What did I say? I say that for instance here, previously we had the ideal transformer. It has primary inductance of 1 Henry and secondary inductance of 1 Henry, right? So let us check. What do we see at the output? If we run this simulation, we see that we have 239 volt, but also we have 215 volt. And then, what do you see? We see that there is a changes of the parameters in all the parts. You see now, the output voltage for the bridge, it's 50.01 volt. That is for AC and for DC. Similarly here, it is 50.3 volt. This is 50.3 volt. So do you see what the input of the voltage regulator? The input of voltage regulator, it is 50.1 volt. But the output is still what? 5 volt. 5.02 volt. That's what I told you, that sometimes some students used to lie in the year simulation. They use ideal transformer and they just say that because the output voltage is 5 volt, then they say we use the step-down transformer. Well, it's not true. Are we together? Are we together? Be careful about that lie, because it's a great lie. So let us restore our previous setting. This one is 2.5. millihenry. So you have to make sure that you use a step-down transformer. And then what do you see? Once we have voltage regulator, we have filter unit, we have bridge rectifier. When you check the measured current, the measured output currents of the step-down transformer, it's what? 15.9 watt milliampere. Previously, if you do remember, it was 0 milliampere. Hello? Previously, the measured value by this AC milliampere, it was what? Milliammeter, it was what? 0 volt. Now, after connecting loads which has internal resistance and consuming some current, then you measure that, the measured AC voltage or the measured AC current, it's what? 15.9 watt milliampere. Something happened. Are we together? Yes. Bina Mungu is Bina Mungi. Okay. So then let us implement the remaining part, which is the first block, which is load. This is, for the load, we need what? We need first of all, resistor. So this is the resistor. Also we need ready LED. Here it's our ready light emitting diodes. And then let us connect them to the circuit. This one. So, but again, we had some other testing points. Let us go to the visual instrument, DC voltmeter. So this is DC voltmeter to measure voltage across the resistor. Then we have another DC voltmeter. This one will measure the voltage across what? LED. But also we need a DC ammeter to measure the output what? The output current. So let us connect there. You have to be careful on connecting the ammeter. So we need to use the C milliammeter. So I think that we have all the testing points. So the voltage across resistor, it is 2.77 volt. The voltage across the LED, it is 2.24 volt. When you add them, you get 5.01 volt. Hello? Look there. Let me repeat. The output voltage is 5.01 volt. Right? Then this one, it's load, consuming current. And this one, it's load. So the potential drop across 220, it is 2.77 volt. The potential drop across what red LED, it is 2.24 volt. So if you take potential drops across LED plus potential drop across resistor, it makes what you get a total output voltage. Are we together? Are we together? Yes. Okay. So let us track our circuit from the beginning before we connected the power bank or the connectors. So the supply voltage 242, the output voltage 12.1. Then you see that now the output current of the step-down transformer 60 milliampere. Why? Because as long as you are adding loads, more loads draw more current from the source. More loads draw what? More current. So it means that's why we have, remember previously, the AC milliammeter measure 0 volt when we had only a step-down transformer. Right? Right now it's 60 milliampere. What happened? Because we added more loads that consuming electric power. Are we together? Are we together? Is it clear? Any question about what we have discussed? So let us check again. What do we have in bridge rectifier? Wonderful. The input voltage of bridge rectifier still the same. 16.97 volt at the maximum. Okay? But the output of the bridge rectifier is 15.3 volt. Previously it was 15.8 volt. Then the input of filter, it is 15.3 volt. But the currents consumed in this network, it is still 0. It is still what? 0. Then the input voltage to the voltage regulator is 15.3. And according to the specification of the LOM 7805, the input voltage, the minimum input voltage should be 7 volt, and the maximum input voltage should be 25 volt. So when you feed more than 25 volts to this LOM 7805, then what's going to happen? You are going to burn the voltage regulator. Are we together? We are going to burn what? The voltage regulator. Okay? Okay, class? Okay, fine. So then, how do we have, or how do we get those connectors? So when we track, remember that if, for instance, we disconnect, what happened here is just the filter. If just we disconnect the filter from this network, then we have the measured parameters as what we had. For instance, if you break the circuits, then remember that these are the measured parameters for the filter. David? Right? Right? So in case that you have drawn the overall schematic circuit diagram, if you want to do measurements of the input and output of each block, you just disconnect the circuit and deal with the part, with a small part. And that's very important, and it's a trick of troubleshooting. Whenever you want to troubleshoot something and fix it or identify the problems, you have to go step to step. Okay? Okay. Is it clear? Is it clear? Before I show you about the power bank, how do we distribute the 5 volt that we have? Do you have any question at that point? Okay? You're welcome. Okay, then Patricia has asked the question, which values are you going to note, to take them as the note in your and fill in the table of results? It's a good question. I have given you 2 types of the table of result. I gave you a table of result for each block. So for the table of result of each block, you have to fill the measured values of each block as a separate block. Then the second type of the table of results that I told you that to formulate or construct it is overall table of result. So in case of overall table of result, you have to make sure that you note the measurements when we have overall schematic circuit diagram. Is it clear or it's not clear? Huh? I know that most of you have overall schematic, have overall table of result. Huh? Yeah, so for overall table of result, what you have to fill is you have to do the measurement for the overall circuit. But for the separate table of result of each block, what you have to fill is what you have been measuring. Are we together? Class, are we together? Yes. Then how do we get these connectors? So if it is clear, is there any other question? Okay. So let us come back to the components. Go to the peak watching. Then write connectors. So let me show you the power bank. Write connectors. Then choose connectors in category. In subcategory, choose these connectors. We call them SIL connectors. SIL connectors. SIL connectors. So with SIL connectors, we have SIL connectors of the different pins. This is SIL connector with a single pin. SIL connector with how many pins? 10 pins. So you can take this one. I just wrote connectors. Then go to the category, choose the word connectors. Then go to the subcategory, choose the word SIL. SI, right? Did you note? Then, let me repeat, because I've been asked, what? So what? I said, go to the library, write connectors. Once you write connectors, I made a mistake, I used double O. Write connectors. Connectors. In category, choose connectors. In subcategory, choose the word, just scroll down until the word SIL. Have you seen it? SIL. SIL connectors, because you have a number of connectors. Then choose a connector with 10 pins. Then once you are done with that, so simply we say that, okay, can have this connector. So you have them here at this point. Then we have the other ones, maybe at this point. Let me just show you according to the general block diagrams that I taught you to draw. I said, attention, look on the blackboard. Or look on the screen. So, this is positive power connector or power bank. You remember it? Okay, how do we connect it? Wonderful. So we have to take the output power from the output pin of the voltage regulator and connect one of the pin. Okay? Then we'll be using the soldering wire to interconnect these connectors. So this is soldering wire. Physically, we used to use soldering wire. Okay? Okay? So there we are going to have 5 volts. And these are the 9 remaining pins will be supplying voltage to the different parts of the electronic circuit. But that is for the positive. Okay? Okay? Then we need also the common ground to power different parts of the electronic circuit. So you just take a jumper and connect it to this terminal. Then use the soldering wire to solder these pins. So here we have a common what? Common ground terminal. That's what I used to draw as power, positive power connector, negative power what? Positive power bank, negative power what? Bank. For instance, if you have one of the components here, let's say that we have what? Let's say we have one of the components, let's say UAO 741 operation amplifier. So this operation amplifier, this one. This is the electronics component. For instance, this is a control, one of the control units. This is non-inverting terminal, this is inverting terminal. But this pin number 7, it's power. So for instance, this one, I can connect it, or I can connect it with the what? With the power bank. So this is positive, so I come and connect it in this what? Let's say that in this second pin, or pin number 9. So when I run the simulation, remember that these connectors are not part of simulation. For instance now, hello, hey! If you run the simulation for this case, then you see that our simulation now has errors. What happened there? Error. For you, I know that you hate errors. But in electronics, we love errors. Before our circuits was running, was giving us measurements. But then now we have errors. What caused the errors? Wonderful. There is a part of the components which we connected in our circuit which does not have mathematical equation behind it. And that is what? 10 pins connectors. Are we together? So you can see that the software also said no model specify J1. So J1 means the first connector. No model specify J2. Where is J1 and J2? This is J1. And the other one is J2. So these models, they don't have mathematical equation. They have just a schematic symbol. So previously your schematic circuit or your simulations was running. But now it's no longer run. Then you panic. No, you should not panic. You have just to check. Okay? So if you want to restore, you just undo. Just undo everything that you've done. Undo, 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 undo. While you are checking it, undo until you don't have J1. Okay, so for this one, let us delete this. So you don't have J1, we don't have J2. So this one, let us delete it. So for that case, our circuit is still running. Mavumba is no longer in the class. It's just writing. Are we together? Eh? So if you want to go back, simple. You just stop the simulation, then redo. Do the redo. When it's limited, then you join the other parts. That's how we think and we work in electronics. Okay? Are we together? Yeah. So this is the system which actually teaches you the concepts of how you can deal with AC power and DC power. Okay? Did you understand the concept? Is it clear? If you understand, ask your neighbor, did you understand it? Ask your neighbor, did you understand it? Ask your neighbor, did you understand the concept? Ask your neighbor, are you going to practice more? Ask your neighbor, will you practice more? Okay, so now it's time to congratulate you. It's time to congratulate you. You have done a great job to understand how to design or how to simulate a linear power supply and do the measurements. 1, 2, 3. Ongera. Imara. Wow. Tell your neighbor, congratulations. Tell your neighbor, welcome in workshop 13. Thank you very much. Be blessed. See you in the next time.
Mungu ibariki Tanzania, dumisha uhuru na umoja wake kwa waume na watoto. Mungu ibariki Tanzania na watu wake. Ibariki Tanzania, ibariki Tanzania, tubariki watoto wa Tanzania.